So in this series of videos about graphs of related functions, given a graph of a function y equals f of x, the following transformations are going to describe how to sketch the related function. If our related function is y equals a f of x, then we're going to get a stretch because our a is going to act like a scale factor. So the stretch of y equals f of x is going to be parallel to the y-axis by a scale factor of a. So we're multiplying our y coordinates by that scale factor, and our x coordinates are going to stay exactly where they started. So let's consider this function here. It has roots at -3, 0, and 1, 0, and it has a minimum stationary point at -1, -5. So if we want to look at y equals 2 of f of x, we're going to scale the y coordinates by 2. So we're going to double all the y coordinates. So you can see that that minimum stationary point has now gone down to -1, -10. If we look at y equals 3 of f of x, we can see that all of our y coordinates have tripled this time. So our original minimum stationary point has gone from -1, -5 to -1, -15. But you can see that the points located on the x-axis have remained fixed because multiplying 0 by 2 or by 3 is not going to have any effect. So when we're applying the graph of y equals a of f of x, it gives a stretch of f of x by a scale factor a parallel to the y-axis, and our x coordinates don't move. So what if we have a fractional scale factor? So let's look at y equals f of x this time with our key points being -2, 0, and we've got 1, -15, and we've got 4, 0. If we look at y equals a half of f of x, we're going to half all the y coordinates. So it means that our curve is now going to go through our roots as it originally did, but that minimum turning point is now at 1, -7.5. So our y coordinates have all halved. If we were looking at y equals a third of f of x, then it makes sense that our curve is going to end up with our coordinates being scaled, our y coordinates being scaled by a third. So our roots again stay fixed, and our 1, -15 becomes 1, -5 as our minimum turning point. So the graph of y equals a of f of x gives a stretch of f of x by a scale factor a parallel to the y-axis. But if we are having a fractional, then it means that it's becoming closer to the x-axis. In the previous examples, we looked at where the scale factor was greater than 1, and our turning points became further away from our x-axis. So if we want to sketch the related function of y equals f of x over a, then we're going to have another stretch, but this time our stretch of y equals f of x is going to be parallel to the x-axis by a scale factor of a. Because this time we're doing y equals the function of x divided by a. So in order to isolate x, we would have to multiply both sides by a. So all of our x coordinates are going to be multiplied by the scale factor. Let's consider y equals f of x being this curve here. And we've got our roots at -2, 0, 1, 0, and 3, 0, and we've got our maximum turning point at -1, 2, and our minimum turning point at 2, -1. We want to find the graph of the related function y equals f of 2x. So we need to consider where our x coordinates are. So if we look at that root -2, 0, if our function 2x is going to equal -2, we need to divide by 2 in order to isolate x to find the new position of our x coordinate for that particular root, and it's going to end up being at -1, 0. So if we have all of our x-coordinates, you can see that our y-coordinates have stayed exactly in the same place because we've stretched our curve parallel to the x-axis by a half. If we want to consider y equals f of a half x, again, let's look at that -2, 0 root. If a half x is going to equal -2, then we're going to have to multiply both sides by 2 in order to isolate x to find the new x-coordinate. And so it's going to become -4, 0. So basically we are doubling all of our x-coordinates in order to find our stretch curve parallel to the x-axis. So the graph of y equals f of x over a gives a stretch of a parallel to the x-axis.